one more, I think, or maybe there's more. I don't know. We're going to find out. But here's where we left off. The last thing that we were talking about was finding heat of reaction. And so you have all this in your notes. And so we were looking at ways that you could find the heat of reaction for an equation. And so we had this one, which was clearly not balanced, but eventually we balanced it. And so we mentioned one way you could do that would be if you're given data, you could take data to experiment and perhaps use, Q lost is equal to Q gained to find that. Another way we talked about, and this is the last way, was maybe you were given steps in a reaction and their heat of reactions, and you could actually manipulate them to find heat of reaction. And so we went through all this mathematics all the way down to the part where we find it, and then we realize we can interpret it for whatever we wanted to use it for. Before we go on to parts 3 and 4, I want to kind of talk to you about why that's okay to do. And it has to do with something called Hess's law. And what Hess's law says, essentially, is that the heat of reaction will be the same whether a reaction takes place in one or many steps. So here's what that means. Oops, sorry, didn't mean to scroll that off the screen for you. Is you've probably seen a reaction diagram here that looks kind of like this. And in a reaction diagram like this represents the reactants. This, by the way, is potential energy. This is as the reaction progresses. This line here represents the products. And so in the case of this particular one, you can see the reactants have more energy and the products have less energy. And so this reaction must lose energy. And in fact, the difference between reactants and products represents the heat of reaction. So if you were to take the energy of the products minus the energy of the reactants, we would get a negative number, which is why delta H would be negative. We also know, just another thing with this diagram, is that from where you start up to the top of the peak is known as E sub A, our activation energy, the amount of energy you have to put in to get the reaction to occur. Well, if we were talking about our reaction of 2 aluminum plus Fe2O3, okay, I can make that bigger, sweet, and it falls apart into product 2. Whoa, my pen totally got crazy on me. Let's fix that. Falls into products of 2 iron plus Al2O3. If that takes place in one step, products minus reactions give us this delta H of reaction. But the example that I did for you, let me scroll back for a second. Ooh, and let's make it smaller. Is I had actually given you 2 possible steps. Saying, well, maybe it took place in 2 steps. And in fact, look here. Here are the 2 steps. Maybe we started with iron oxide and it broke apart into iron and oxygen. And then maybe the aluminum reacted with that oxygen to produce aluminum oxide. So maybe it actually happened in 2 steps. Well, how that would play a role on this reaction curve is my reactants would start the same amount of potential energy. But maybe there was a first step, and then maybe there was another step, and then I hit the product. So here are my reactants, here are my products. But notice that the difference between reactants and products is the same heat of reaction as here. And so that's why it says delta H. It doesn't care if it takes place in 2 steps or if it takes place in 1 step, you're still going to get the same heat of reaction. So ultimately, if you know the heat of reaction for this and the heat of reaction for this, if they add together to give you what you want, that heat of reaction will be the exact same as if I did it in 1 step, for example, maybe in a lab. All right, so that is number 2 when we're manipulating the steps in the reaction, and that's kind of how that works. All right, number 3 would be if you are given delta H sub F. This is known as heat of formation. Here's what delta H sub F is. Delta H sub F, the heat of formation, is the energy change that's associated with producing 1 mole of a compound that's important, I'm going to underline that, from its elements. And since it's very specific that it's producing 1 mole of a compound, not 1 mole of an element, one of the things we have to know is that delta H sub F for an element, I don't care if it's a diatomic or not, is always 0 kilojoules per mole. Okay. So here's what that means. There's actually a table in your book, and it certainly wouldn't hurt to eventually look at that table. I'll point it out in a second here. But if you look on the table in your book, it's a huge table, and you look up the delta H of formation for AgCl, the heat of formation for that is listed as negative 127.1 kilojoules per mole. What that literally means is that if I create 1 mole of AgCl from its elements, silver and chlorine, and I'm going to have to put a half here because by definition it's 1 mole, so this has to be a 1. The delta H is negative 127.1 kilojoules. That could be for 1 mole of silver chloride. It could be for a half a mole of chlorine. It could be for 1 mole of silver. We could interpret it however we want, but that's what it literally means. So how does that relate to this equation that we have been doing all along? Here's what I want you to do. Pause the video. Get your book. Find the heat of formation table. Go ahead, I'll wait. No, I mean really, go get your book. Seriously, get your book and open up to that table so you know what I'm talking about. Pause the video. Do it. All right, I know some of you are still watching, but I'm moving on. If you didn't pause the video, shame on you. Here's what we need to know. If we want to use heats of formation for that, here's the equation for it. The heat, delta H of a reaction, is equal to the sum of the heats of formation of the products minus, that is the sum, that was a really weird epsilon, the heats of formation of the reactants. So some of you guys may have learned, like this epsilon, it refers to the sum of. So you have your book out, right? And you're looking at this large table in your chapter, and it's got heats of formation all over it. So here's what we're going to do. We're going to do by example. According to this, I'm going to take the sum of the heats of formation of my products, which is these guys. So I have 2 moles of iron times the heat of formation of iron. So you could peek at your table and find that iron's not listed because the heat of formation of an element is 0. So don't be that person on the test who comes up to me and I give you a heat of formation table, because I would, and says, Mrs. May, iron's not on there, because I will refuse to answer you. So it's 0 kilojoules per mole. Plus, I have 1 mole of Al2O3. And here's where you look on the table. This one's there. See if you can find it. When you do, it's negative 1,675.7 kilojoules per mole. That is the heats of formation of the products. Then I'm going to subtract the heat of formation of the reactants. So minus, here are my reactants. I have 2 moles of aluminum, which is also an element, so that's 0 kilojoules per mole. Plus, I have 1 mole of Fe2O3, and this one we can look up. Go ahead, find it. And it is negative 824.2 kilojoules per mole. And that is the products. Notice like the moles all cancel. So my units that remain are going to be kilojoules. And when I do that, 2 times 0 plus 1 times negative 1675 minus, and don't forget your parentheses here because that's where you screw stuff up, 2 times 0 plus the negative 824.2, your delta H for this reaction is negative 851.5 kilojoules. The exact same thing that we got when we rearranged all this, right? So it's negative 851.5, which we could then interpret. So it's negative 851.5 kilojoules per 2 moles of aluminum, or negative 851.5 kilojoules per 1 mole of iron oxide, or negative 851.5 kilojoules per 2 moles of iron, or per 1 mole of aluminum oxide. And then we can use that in a problem, which you will. As you work through problems, sometimes you'll use the heat of formation table to get this number. And then you'll need to interpret it based on, oh, the problem gave me 10 moles of aluminum oxide. Okay, then I'm going to interpret this for aluminum oxide. Great. So you have to just make those decisions. All right, that ends us for this one.